Hello, it's Keith here, and this is lesson 3 of the so-called MinTile series of my 68000 assembly programming tutorials. MinTile is a software tile map system that I've written for all of the systems on the Z80, 6502 and 68000. Now, the benefit of this is that it works in software on a system like the QL that you can see here, which has no tile map functionality, but it uses the tile map capabilities of a system like the Genesis or the Neo Geo, where the sort of tile map way of working things is more mandatory, really, rather than bitmaps. So it gives a constant way of doing things across systems with very different capabilities. Now, what we're going to look at today is the code that actually handles the removal of the sprites. Now, you can see we're moving our character. This is the Chibico mascot here. We're moving the character around the screen, and the object has to be removed. It's a software sprite. It's not a hardware sprite on any system really, but it's being simulated with a tile map, and it's being removed as it's moving around, and it's that removal code that we're going to take a look at today, and also a few other small helper functions that sort of help out the code with regards to that removal. Now, the code we're going to look at today is multi-platform code, so this works on every 68000 system, and there's a system on the other Z80 and 6502 systems that works in the exact same way. This is designed for porting across different platforms, so it works in a very common way, just with the register numbers and names different on the different systems really. Let's go over to our code and let's take a look. Okay, so here is the code we're going to be looking at today, this remove sprite part of the minimal tile code. Now, at the very start here, at the start of the remove sprite routine, we are first checking the refresh tile flag. Now, this is a flag within our sprite object. We pass the sprite object in A4. This is a set of data that defines various things about the sprite, its position, its size, and whether it needs to move or not. Now, if the refresh tile flag is 0, then the sprite hasn't moved. It doesn't need the background redrawing. So in that case, we're simply going to return. That saves some time in the case that the sprite hasn't changed. Now, otherwise, we're going to load in the various parameters. Now, we're basically simulating the Z80 kind of functionality here. So we're loading in various bytes into our parameters, and we're just clearing all the registers here to make sure there's no garbage left over there. So we're loading in the old X and Y position, the position the sprite was in before it moved, because we're assuming it's changed its position. So we're loading in the old position so that we can remove the sprite from that position. Now, we've got these options regarding X smooth move and Y smooth move. Now, on some systems that are using a hardware tile map, we're moving in 8 pixel blocks, and so we're always aligned to a complete number of tiles. However, if we allow smooth moves, we can move in up to 2 pixel blocks, as low as 2 pixels. The coordinates don't allow single pixel movements, that's why it's up to 2 pixels. And in that case, if we're sort of 2 pixels into one tile, that means we're 1 tile over the entire width of our sprite, because we're still in the first tile, but we're now in an extra tile after the width of the object in tiles. So in that case, we're adding 1 full tile. 4 logical units is 8 pixels. That's 1 tile. So we're adding 1 tile to the width and the height if we're allowing those smooth movements. So say it basically depends on whether the system is capable of it, depending on the memory alignment of the bitmap screens, or if we're using a hardware tile map to draw our simulated sprite objects. So that's what we're doing there. Now, what we're going to do next is we need to work out the actual amount of the sprite that's on the screen. If our carrot sprite object is in the corner like this, well, it's going to be covering a smaller area of the screen, and so we're going to need to adjust accordingly. So we're doing our do crop here, but we don't need to care whether the sprite object is flipped or not. It makes no difference to our removal of the background, so we're using the simpler no reverse version there. Okay, now we've got our size and our X and Y position in logical units, pairs of pixels, but we want to convert that to a number of tiles and a tile position because we're working on the tile map here. So we've got this very simple function here, do crop logical to tile. We'll see that in a moment, but basically it just divides the X and Y width and height by 4, converting from pairs of pixels to numbers of tiles. So that's what it does. Now, what it also does though is if the height was 3 logical units, or the width was 3 logical units, that's under a tile. A tile is 4 logical units, and we always work in multiples of tiles. So if either the width or the height has become 0, we're basically going to set the 0 flag to true here, and in that case we're going to return because there's nothing we can actually viably draw to the screen here. So that's what we're doing there. Now, what we're going to do next is we're actually going to calculate the position within the tile cache. Now, we're not drawing straight to the screen. If our object is here, we want to cover it up with tiles, but we need to work out the position within the cache that we want to draw to. The cache is the changes that need to be drawn to the screen in the next refresh procedure, and it's just a 32 by 24 grid of tile numbers. So what we're doing here is we're loading the address of the tile cache. We're setting the width, 32 tiles, the width of the screen on all systems here, And we're running this shift tile map routine here, which will move the memory address in A2 here, and it will adjust it accordingly for that X and Y position, so that A2 now points to the top corner of our area that we want to remove. So we're doing that to the cache here, that's the destination. Then what we're doing is we're doing the same thing to the tile map 2, which is the source tile map. Now this is the default background that we want to draw back into the cache and show on the screen to remove the sprite that's on screen. Now the tile map 2 is bigger than the cache. The cache is 32 tiles, 20 in hexadecimal. The tile map 2, the actual the visible, what should be behind the sprite, is actually wider than the screen. It's 36 tiles. There's 4 extra tiles so that we've got a scrollable area. So that's 24 in hexadecimal. That's why we've loaded that there. And then we're calculating the scroll offset here, and we're adding that to the tile map base here, and that is calculating any scrolling, because obviously if our tile map is scrolled, then we need to draw the correct scrolled tiles back to the screen to remove our sprite. And we're using shift tile map a second time here, and that is going to affect the source data in here, and we've already affected the destination data up here. So now we've got our source and our destination. So the last thing we're going to do is we're basically going to proceed to draw all of the tiles from the source to the destination for the width and the height of our object on screen. Now, although our object is, the width of our object will depend on the actual sprite size and its position, you know, it becomes half the width if it's half off the screen. We, of course, need to move by the entire width of the cache as we're moving through the cache's memory. So we're loading 32 into D7 to do that here. What we're then going to do is we're basically going to sequence through the entire width of our sprite object here, and we're going to load a single byte from the source tile map, that is the tile map 2, to the destination tile map, that's the cache, and we're going to repeat until we've done an entire line, and then we are going to then move down one line of the tile cache by adding D7, which is 32 up here, with the width of the tile cache, to the destination, and then we're just going to repeat for all of the subsequent lines. So this is drawing the data back from the original tile map back to the tile cache, and the tile cache is processed during the next CLS. Any non-zero byte in that tile cache is an update that needs to be made to the screen. That's how this version of the code does things. So that's the routine that actually draws the background back to the screen. Now what we're going to look at next is just a few helper functions that do those kind of jobs. The first one is that shift tile map routine. Now the way this works with its registers may seem a little bit odd. The reason it works this way is it's a mirror of the Z80 code, and it made a lot more sense on the Z80 code. On the Z80 we had a DE and a HL register. HL is more powerful than DE, more capable, and I use A2 as the equivalent of DE, and A3 is the equivalent of HL. And so that's why you see some strange things like this routine takes its parameter in A2 and returns its parameter in A3, and that's because this code is a direct port of the Z80 version, and so that's why things work like that. So what we're doing here is we are moving our source tile map address into A3 here. We are then masking the width to make sure we've only got a single byte in D7 here. We're then moving our Y position into D0 here as a single byte, and then we're multiplying the Y position by the width of the tile map in bytes. And so this is calculating the Y offset in the tile map for the line that we are actually wanting to look at. And we're adding that to A3. What we then do is we then add the X position. Now the tile map is single bytes, so we're just adding the X position as a count of tiles. We're doing that here, and then once we've done this, A3 now equals the memory address of the XY position we specified, which in this case will be the top corner of the sprite object. And as I said before, we do this to calculate the destination position in the cache and the source position in tile map 2. Another routine we saw before was do crop logical to tile. Very simple routine. We're just converting from pairs of pixels, logical units, to tile count, which is dividing by 4 basically. So we're just doing bit shifts here to D1, D4, that's the X and Y position, to effectively divide them by 4 here. And then we're doing a bit shift to D3. D3 is the width. We're checking if that's resulted in a 0, and if it has, we're returning, and that will set the 0 flag to true, basically saying there's nothing you can viably draw here, give up. We then, if that didn't return in a 0, we're doing the same to D6, and then we're returning, and so of course if that resulted in a 0, the 0 flag would also be set, and again it's a command to give up. Now the final thing we're going to see today is the change scroll routine. Now the change scroll routine was a way I came up with of resolving an issue with regards to the performance. This routine doesn't use a double buffer. Some systems it's not convenient to do so, like the QL. Using a double buffer actually means you can't use the operating system because it wipes over all the operating system RAM, because it seemed like a smart idea to the designers to have the second screen buffer use the same memory. I don't understand that, but that's what happened. Anyway, so we're going to have to try and work around the fact that we've no double buffer, and that's why you can see some flicker on the sprites as they move. Now, the problem is when we're scrolling. Now, when we're scrolling, we're redrawing the entire screen. You can see we're scrolling our background here, and it looks quite nice, and it's reasonably fast. Now, we needed to basically reduce the amount of calculations we were having to do to redraw that screen, and so what we wanted to do is make sure we're not updating more tiles than we need to draw the new version of the screen. Now, the scroll that you can see here, it's always moving in entire tiles. There's no half tile or per pixel movement. So it's very crude, but it's just a simple scroll. Now, how are we actually going to do this? Well, what I decided was rather than just redrawing the entire tile map 2 to the tile cache, which would have worked, but it would have been slow, we could compare what tile is currently on the screen at a position and the new tile after the scroll, and if they're the same, well, the new position is going to show what the current position is already showing, and in that case there's nothing to do, so we won't do anything. So that's what we're doing here. Basically what we're doing here is we are specifying two source tile maps which will be different tile positions within the same tile map in A1 and A3, and then we're specifying a destination tile map in A2, and that would be the tile cache. So we're going to compare these two tiles. If they're the same, we're going to do nothing, and if they're different, we're going to update the cache and instruct basically the drawing routine to draw the tile again. So that's what we're doing here. We're loading a byte in from A1 here into D0. We're comparing the byte in A3 to D0. Now, if those are the same, well, the tiles are identical, there's no need for another draw, and so we're just skipping along. If they're different, we're writing that tile number to the tile cache in A2, and that's basically instructing a draw to occur when we do our clear screen. Okay, we're then just moving along the tile maps, repeating till we get to the end of the tile maps. Now, once we've done an entire line of 32 tiles in our cache, we need to then skip the 4 extra scrollable tiles within the tile map 2, and so it's hard coded for the 36 wide tile map here. So we're adding 4 to the tile map 2 addresses here, the 2 comparison addresses here, and then we're repeating for the next line, and then we're returning. And that's how I'm doing that animation, that reduced amount of drawing, and allowing that fast animation for the scrolling routine. So there we go. So that's all we're covering today. I mean, as I would say, you can go to more website down the source code and the build scripts, and you can use this code if you can in anything of your own. You're welcome to do so. Now, what I'm planning to do later is a more advanced version of the tile map routine. We can see here, this is known as MinTile, minimum tile. Very simple tile map routine, quite limited. And I'm hoping to write a more advanced one called Max Tile, which does more things like it can do Y flip and it can do more transparency and things. It allows for more tile numbers. So this is really a very basic tile map example. It might be enough for what you need, and as I say, even if it's not, you're welcome to just use it as an inspiration and an example. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.